Okay, so we take off from where we had left in the last class, and we'll be using Castigliano's theorem and learning how to use Castigliano's theorem and in this class today. Okay, so let's consider a system of two springs which is shown in this figure, and we shall use the Castigliano's theorem for solving this particular problem. So let's see. Uh, you have to obtain the deflections delta 1 and delta 2 for each of the two springs, and given that you know these external loads P1 and P2, so you have to find the extension delta 1 in this spring, extension delta 2 in this one over here. Okay, and that's what you have to do. So let's see how you can solve this. So you say that there has to be a force balance in the x direction. So the force in the spring 1 will be equal to P1 plus P2. I'm showing it as a scalar because the direction of it is very well known. It's in the outward x direction. Okay, and the force in the spring 2 is equal to P2. Okay, so once you do this, you will have the total elastic energy in both the springs will be P1 plus P2 whole square by 2K1. Clearly it's a linear spring, okay, because only in linear spring will this Castigliano's theorem work. Okay, the complementary energy and the potential energy are the same. And similarly, now you would write the potential energy for the second spring, that would be P2 square 2K2. Okay, so now you would use Castigliano's theorem and write that delta 1 will be equal to dou U by dou P1. Similarly, delta 2 is equal to dou U by dou P2. Okay, and that's how you would get delta 1 and delta 2 in this problem. So this was example 2.11, and that's how you can simply use Castigliano's theorem to solve it. Okay, so this is also called the energy method of solving any problem in solid mechanics, and this is a good start. Okay, one of the other things which is implicit in this solution, that it satisfies all the requirements of steps 2.1. 2.1 was about the force balance. Okay, it was about the geometric compatibility and the relationship between force and deformation. So it is easy to see from this that all these three things are actually contained within this method. You are not missing out a step, any of these three things. Okay, you are not explicitly going step by step, but all those things are implicit in this method. So you should be able to verify that. Please think about it. Okay, why this method includes all these three things. Okay, so now let's consider example 2.1a. Okay, and in that also you have to use Castigliano's theorem to find the deflections. So let's first recall what example 2.1a was. So that we don't have to go back to that again. There you go. This is example 2.1. Okay, and what I'll do is I'll try to use Castigliano's theorem here itself. Okay, and one thing which I'll do is I'll perhaps use a different ink. Okay, so I'll maybe use a green one over here. Okay, so I'll try to use the green ink over here, and whenever you look at it later on, you can know that the greening means the Castigliano's theorem were used. Okay, so in this particular case, I mean, you have already done most of the analysis. So F1 plus F2 is equal to F, not shown as a vector because the directions are already shown, and that would give you a relationship between F1 and F2, and F1 or FA perhaps is a correct way to write, is the force in spring A, this is this force in spring B. So FA plus FB is equal to F, and the total potential energy is UA plus UB. Okay, and that would be equal to FA square by 2KA plus F minus FA whole square by 2KB. And using this, you can just write the Castigliano's theorem and say this is the delta A, which is the compression in spring A, and then you can also write delta B to U by 2FB. Okay, but since delta A is the same as delta B, geometric compatibility of this problem, you can find out what these values will be. Okay, so you will get rid of essentially FA and FB in this case. So that's how you can find delta in this case. One of the other questions which you should think about in this problem and in this solution given in your textbook is that when you write the total potential energy, why are you missing out, or should you miss out, the potential energy of the block? Okay, this piston, sorry. Think about why you should or should not include it over here. Okay, and for this you will have to clearly go through the derivation of the potential, the energy analysis, which was the Castigliano's theorem. So please think about it, and you're free to discuss it with me whenever you think you have figured out a good answer to this. Okay, whether you should have it, if you should have it, if it's okay to ignore, why is it okay to ignore, and so on. Because clearly the piston is also coming down. Okay, so there is definitely a potential energy associated with that. So see if you can figure this part out. Okay. Okay, now let's come back to example 2.12, and this was, if you recall, this question. It was example 2.4 over here, and we were trying to solve this problem using Castigliano's theorem. Okay, so I request you to please revise this problem what we had discussed before as an example 2.14, and then we'll come back to example 2.12 where we discuss this. Okay, so let me just switch back to the color. Okay, there you go. Okay, so in this particular problem, I mean, we have so the total stored, and so we want to solve this problem of finding the deflections of this particular case. You want to essentially find the deflection of this point D. Okay, and that's what you want to do. So let's see how this can be done. You want to add the together the total energies, even though one member is in compression and the other is in tension. Okay, so one of them is in, I think BD was in extension and CD was in compression, but the potential energy will still be U1 plus U2, and that can be written as P1 square by 2k1, sorry. Okay, this is p1 square by 2k1 plus p2 square by 2k2. So you have a p over here, you have a p over here, and you have a root 2p over here. Okay, these values we have already sort of found out. Okay, and then you can directly find what the delta p would be, right? That would be dou u by dou p, and you would get the answer of delta p. Now there is one more part to it. If you remember the solution of this problem, point D did not just move vertically downwards, it also moved in the horizontal. So the D dash was somewhere over here. However, by doing this, you have just found out the vertical component of it. Okay, you have not found the horizontal component of it. So does this mean that Castigliano's theorem will only work if you have a force acting in line to the displacement you are trying to find? The answer is no. Okay. So in this case, for example, you want to find the horizontal component of this, okay, delta q, and so the way you proceed is this: you include a fictitious force q, okay, like this, then apply the Castigliano's theorem, and later on put q is equal to 0. That way you can find delta q. Okay, so you want to do this, you write u is equal to 2p square by 2k1 plus, so you are trying to solve this system now after this fictitious force, and then you have 1 plus 2k2 p minus q into whole square. One of the other things is, every time you add a q over here, you have to put a minus q over here in this direction. Otherwise this CD will not be in equilibrium anymore. Okay, so that's why you are putting a minus qa over here as well. Okay, so that would make the total energy of this. So the forces in the individual bars which are required to satisfy the equilibrium requirements are indicated, and now the total energy in terms of the loads P and Q is given in front of you. All you have to now do is write delta Q is equal to dou U by dou Q is equal to 0 minus P minus Q by K2, but q was actually equal to 0. Okay, there was no q in the original problem, so this would imply that delta q is equal to minus p by k2. Okay, so this can be one way to find it, and hence you now have a vertical displacement and the horizontal displacement, and you can combine both of them to find where the point D would have actually moved. Okay, so please compare these answers with the earlier methods and see how easy or complicated this method is compared to the other one. Okay, but keep the answers in mind as well when you do so. Okay, so that's one part of it. Now let's look at the other. Okay, so that's now let's again briefly discuss. Okay, we won't go into this. This is the same trust problem which we have discussed before, and by this time I assume you have read about the computer application of this problem, and you know, and perhaps have actually coded this in MATLAB to get the results which your textbook says. So that is a prerequisite by this now. So you just to clarify that beforehand. You want to do what you want to do now is you want to use Castigliano's theorem to solve this problem. Okay, so the methods remain exactly the same. Okay, so if you assume that your trust structure is made up of what, 9 members as indicated in these diagrams, 1 2 3 4 5 6 7 8 9. You want to find the stored energy in all of them. So in each one of them, the energy will be Fi Li square by 2Ai Ei. Okay. The total energy clearly would be I going from 1 to n. So when you code in a computer, you already know that, I mean, the value of n is 9. Okay. But we are just writing it here for the most general trust structure, so that you don't have to confine your answer to this trust structure only. Okay, so you want to now find the deflection. Okay, any external load P, it can be actual or fictitious. Okay, in your problem, the actual force is this, but you still say you want to find the deflection of this particular joint. So there is no actual force, so you will consider a fictitious force like the previous case and proceed. Okay, so this you will find out by saying delta P is equal to dou U by dou P, and you should follow this method. Okay, and I mean, you will have to create fictitious forces like you have done over here. Okay, like you have done over here. So that is how you can find the values. So please go through this and don't skip it before you move ahead in these discussions, because they'll keep on coming again and again, and they'll trouble us as long as we clearly don't understand these. Okay. We now move to the third chapter of this textbook, and it is about the forces and moments transmitted by slender members. That's what it is called, and we'll discuss this chapter because of the applications it will have in the entire course to follow. Okay. Okay, so let's sort of motivate what we want to do over here, going through the section 3.1 of your textbook, which is the introduction. So in the previous chapter, you have considered the fundamental basis for the study of mechanics by the 3 steps of 2.1. Remember, force equilibrium, geometric compatibility, and the relationship between force and deformation. So it was true that the consideration of forces, deformations, and force deformation are all required in the analysis of deformable solids. It is also true that there is a depth of sophistication in each of these considerations, which we have not actually yet considered. I mean, we took the most simplest cases, so that force equilibrium was easy to do, geometric compatibility was easy to do, and so on. But the engineering problems will actually be much more complicated than that. So in this and the following 2 chapters, which is 4 and 5, we shall actually re-examine the significance of these steps 2.1, which is the force equilibrium, geometric compatibility, and the relationship between force and equilibrium. Okay, and then we will lay a foundation for the subsequent studies of solid mechanics. Okay, so in this chapter, which is chapter 3, we will only be concerned about force and equilibrium. Okay, we'll leave out the other parts for the later chapters in 4 and 5. I mean, the deformation and the relationship between force and deformation. Okay. Now let's sort of look at why we want to study this topic. If you look critically at any engineering structure, like a bridge or an automobile or a house, you will note that a large portion of the load carrying members can be classified as something called a slender member. Any engineering structure, I mean, if it's too hard to look at an automobile or a bridge or a house, you can look at a pen, you can look at any other structure. Most of the load is carried by a slender member. Slender member, you mean that the length is much greater than any other dimension. We have already discussed this once. So your pen can be taken as a slender member, and according to the author of your textbook, it must be at least 5 times. Okay. Normally it is much larger, but at least 5 times is what you go with. So this brings us to members of engineering structures, which can be called as a beam, a column, a shaft, a rod, and so on. Okay. So these are all slender members, and they have their names because they are different in what they are supposed to do. For example, a shaft is meant for a rotation. A rod is meant for extension or compression. A beam is meant for bending. A column can buckle. Okay, so there are many applications, and you will see all this being used. The only thing common to all of them is they are all slender members, meaning the length is much larger than any other dimension of the structure. Okay, so in the previous, so there are many other things which you can do with a slender member. You can pull or push. So I am not writing them separate because they are actually the same thing. Okay, they can be bent, you know what a bending is, or they can be twisted. So we have already considered the tensile and compressive loadings along the axis of the members in all the examples which we have discussed before this. Now you want to study these two things. Okay, this you have done enough in the earlier chapters. This is a new thing which we want to deal with right now. Okay, so let's sort of begin this discussion, and before that we'll have to learn about some of the methods through which you can learn about bending and twisting. So the general method for determining the forces and moments acting across any section of a slender member which is in equilibrium is to imagine a hypothetical cut or a section across the member at the point of interest. What the statement means is this: you may have any solid body. I am showing it with an ugly figure so that it's your thought or your understanding is not restricted to the shape. So when you say that you want to have a point of interest, let this be a point of interest. Okay, anywhere in this solid, and you want to find the forces and moments acting across this. So what you do is you will have to cut this through a hypothetical cut. Okay, it's a hypothetical cut or a section, and then you only consider one part of this, maybe this part, maybe the other one, and this is what we'll be using for our analysis in the remainder of this course. The only thing now which you should be able to appreciate, There are infinite possibilities of planes which you can use to hypothetically cut your solid. Okay, I mean, this is other possibility which is passing through the plane, this is other possibility, and so on. So each one of them will hypothetically cut this solid into two separate parts, and hence the orientation of this plane plays a very important role in how we study forces and moments in a slender member, specifically to this chapter and any solid for that matter. Okay, so once you take sort of this, any part of this hypothetically cut solid, then you can isolate them and then apply the force and the moment equilibrium on that point across that section. Okay, so only for convenience, you resolve the forces and moment into components normal and parallel to the axis of the member. Now, this is what you should be looking at. This was clearly a member, a long, slender member, and you have hypothetically cut it at this plane. Okay, and then you have defined the x, y, and z axis along the orientation of your cut. Okay, so this was something which you did after, and when I say cut, it was an only hypothetical cut. In reality, you don't start cutting a solid. Okay, this is just a visualization which you have to do. Okay, so in this case you have the x-axis which is along the axis, which you can see over here. It's along the axis, and it has been oriented so as to coincide with the longitudinal axis of the member. So you know now the y and the z axis lie in the plane of the cross section. So the choice of their particular orientation within the cross section usually is governed by the shape of the section or by the direction of the transverse loading being carried out by the member. So normally you have a plane which has been, say, hypothetically, a plane has hypothetically cut it perpendicularly. So you will have x-axis along the axis. So this is the first thing you should do. Make the axis of this slender member as the x-axis. Okay, then based on the loading or the cut, you can have your y and z axis accordingly. So this is something which you should get used to doing. Now let's look at the notations which you see over here. So if you have a notation f I j, I in this is the plane and j is the direction of force. Okay, so simply said, f of x, y, so the plane which you see over here on this particular plane, this plane is actually x equal to something, right? X equal to 2, 3, a minus 1, whatever, right? If you have to write this plane, and that's why it's called x. And this y is the direction of the force. So this fxy is over here. Okay, so it acts on the x plane in the y direction. Similarly, fxx acts on the x plane in the x direction, and similarly fxz acts on the x plane in the z direction over here. And similarly you can have many other combinations. Acts on the z plane in the x direction. So unfortunately in this diagram you don't have a cut across the z direction, but this notation will come in handy later on. So this is on the z plane in the x direction, and the same can be done for moments. Okay, xz, the moment acting on the x plane in the z direction. Look over here. Okay, And you have also learned about the inertia terms perhaps in your earlier course in mechanics. This was also meaning the same thing. On the x plane in the x direction, on the x plane in the z direction. So this is one notation which you should consider, and it's always positive if outward normal is there. Okay, so these are all positive. I mean, this is a positive number. Okay, so there are names to this. For example, the fxx. In this particular case, you will have fxx is the axial force. Fxy, fxz is called the shear force. Okay, and mxx is called the twisting moment. I hope you can see why it is the twisting moment. Try twisting a pen. Try twisting the pen which is with you, and you will see that you apply the moment in the direction which is shown by mxx. That's why this is called a twisting moment. And mxy and mxz are called the bending moment. This is also, you can see, if you are trying to bend your pen, depending on which direction you are trying to bend it, you will most probably be applying mxy or mxz sort of a moment with your hand. So you can easily visualize why it is called bending, why it is called twisting, and so on. So you will see that fxx is also written as f or fx, just because it's easy to write it that way. The shear force is written as v or vx or vy, depending on which direction the shear force is acting. Sorry, vy and vz. Okay, whether it's a y in the y direction or in the z direction, but the plane is fixed, which is the x plane. Twisting moment is written as mt. Okay, or it can again have its own direction of mtx, and bending moment is written as mb or mby or mbz, depending on whether it's in the y direction or the z direction. This is the most general three-dimensional case of studying this. Okay. So right now, I mean, these all symbols will take a much greater and dynamic, so to say, form, a more fascinating form in the later chapters, which is chapter 7 and 8. Right now, we only want to find the magnitude of these. Okay, we want to sort of, in this chapter, we want to find the methods so that you can find a value to it. How that value is related to concepts of stress and deformation will come later on. Okay, so there is also some sort of a consistency which we follow. Okay, so when you write, for example, a tensile force, and when this is how you have virtually or hypothetically cut this. and you call this as S, call this as S dash. And if you show fx, which is outward normal, positive in this, the other fx has to be like this, because of Newton's third law, because this particular intersection is in equilibrium, and it is also satisfying the fact that it is positive, since a force component in the negative x direction acts on a, so let's see, on the section S, fx is positive axial force, since a force component in the positive x direction acts on a cross section whose outward normal is in the positive x. So the outward normal of this is in the positive x direction, hence this is positive. On the section S dash, fx is also positive axial force, since a force component in the negative x direction acts on a cross section whose outward normal is in the negative x direction. So the important part about these two lines is that you cannot individually see a force. You have to see the outward force with respect to the surface on which that is acting. So it is positive in both the cases, because in both cases fx acts in a direction which is along the outward normal, okay, and that's why it is positive. So in the other case, S dash, also it is positive, since a force in the negative direction acts on a cross section whose outward normal is the negative direction. So these both of them are positive. So this convention must be clear to you, and you have a paragraph on your textbook about this. So a positive force or moment acts on a positive face in a positive coordinate system. It also acts on a negatively directed component acts on a negative face. So you have a positive force acting on a positive face, you have a negative force acting on a negative face, and hence both of them are positive. Okay, so the last part before we actually start moving on to our actual solution of the problems is this. Figure 3.1, which you have, figure 3.1, it shows you a general case where 6 components of forces and moments act across a section. So 3 forces and 3 moments. This is the most general case. However, most of the times, at least in the study which we do, all the forces act in one plane. I mean, we have already seen this. So it's a planar system. And if that is the case, you have your simplification in 2 dimensions like this. So x-axis is along the axis, longitudinal axis of this member, and there is a force F. Remember, it is coming from over here, okay, Fxx or F, and the shear force will be in this direction, which is V or Vy, okay, because you have your y-axis like this. There is no Vz because all your forces lie in one plane, which is the xy plane. So Vz, if you take, it would be in the other plane. So we are taking the simple case only in which Vi acts. Okay, and then you will have a bending moment, which is Mb, and that would be Mxz actually. Okay, so this is Mxz. In this, the forces lie on this plane, but the moment clearly will be in the plane perpendicular. So you have only 3 components. So you had 6 over here, 3F plus 3M. Here you have 3 components, 2 forces plus 1 moment. And this is what we'll be using for most of the course which we have. It's not that the three-dimensional problems are harder. It's just that they will take slightly more time. But it is very easy, and there are cases where you will have to convert all this two-dimensional knowledge into three-dimensional, but it's very easy and straightforward to do that. So, but all our learning and application of concepts will be across this two-dimensional simplification only. So speaking of that, let's move to this first example 3.1, and we will see the methods which are actually used to solve this problem. The methods broadly are the same. You have the actual problem, then you create a model out of it. You isolate the main structure, show all the forces and so on. Second part is to apply the equilibrium, which is the force and the moments. And then you have to cut the member at a section of interest. Isolate one of the segments and repeat step 2 on the above, which is the equilibrium of forces and moments. We have actually already done this in some problem before, in which you had to find the actual axial force on a bar. So we took it at a distance x and virtually we had cut that. So now we'll do it in a much more rigorous way. Okay, so consider a beam. Okay, this is a beam. The first part is about a beam is that it bends. Okay, right until now you have not taken a beam. You took a bar, a rod, which were all either extending or compression. A beam can bend. That's the first thing which you should learn right now. Okay, now that is shown in this figure A. The beam is there, and it is desired to find the forces and moments acting at section C. So you have a section C. You want to find the forces and moments acting on this section. So remember, there are two forces and one moment. That is what you have to find at C. It's for because it's a planar problem. So you have A and B as its hinge. You have a weight W which is hanging at this distance A from small a from capital A, and the length of the beam is L. So this is how you have the problem in front of you. So let's see how you can solve it. You have to consider some sort of a force at A and B. So this is the actual problem as we have discussed. Now you want to have a model of it. So here is how we have drawn the model. We have shown the weight, this W as it is. For the supports, you have taken force both normal and tangential, in both the cases. Okay, this is just to say that the force acting on B is somewhere like this, FB, and the force acting on A is somewhere like FA, so that it has both the horizontal and the vertical components. I'll just remove this. Okay, so this is the most general form with the normal and a frictional component. So normal and the frictional components of the forces will be acting at A and B. Now at this point we don't actually have much knowledge about the magnitude and sense of these friction forces. Okay, in the sense we don't really know what direction they will act and so on. And remember, these arguments we have made before in earlier problems. So like the step ladder problem, remember we had the step ladder problem. Okay, the human was standing and then there was this, I think you wanted to find the force in this member. And so like in this particular problem, the sense of the friction force depends on the previous history of the system. If you recall this, I mean, maybe I can go back and just show you where it was. here. So in this one, there is a history associated, in the sense if the ladder was opening or was it closing, then the friction would act in different ways. And we had already gone through those discussions in this problem. Okay. So if there's any requirement to refresh your memory, now is the time to do that. Okay. So let's come back to where we were. Okay. So the sense of the friction depends on the previous history, and so it will happen in this case. We can say that the friction forces are limited by the static coefficient of friction. So that we already knew from our Coulombic law, that the friction force is limited by this mu n, where mu is the static friction coefficient. When the coefficient of friction is small, we can be satisfied that the friction forces will be small compared with the normal forces. So here's the idea. The Fa at its maximum will be equal to mu Na or Nb, whichever way you take. Okay, so if this value is small, okay, then the friction can be then the friction Fa will also be small with respect to Na. And that is the reason why we are ignoring friction and only showing the vertical reactions over here. Okay, so this is the reasoning behind it. Let me make something very clear. When you say this, it does not mean that the friction is actually acting at its maximum value. Okay, the friction may be acting at a very small value, but the maximum value is this. And when you say the maximum value is this and the friction coefficient is small, so compared to Na, Fa will be in general very small, and hence it is reasonable to ignore that and move ahead with this. We do not say that there is no friction, it's just that we find it reasonable to ignore it for now. Okay, so this provides our first framework to solve this problem, this diagram C which you have, and so that only reaction forces at A and B are in the vertical direction. Okay, we have also neglected the weight of beam. The argument is that it must be very small compared to W. Okay, and that's why perhaps we are ignoring the weight. And this is actually true. I mean, if you consider any engineering structure around you, like a bridge or I mean a pen, for example, if you are applying a point load on it, the weight of the pen will be very small compared to the force which you are applying on it. If you apply it like a beam, like in this particular case which is shown in over here. So that's the reason you can ignore the weight. Now again, you may have done this in your mechanics problems, so you now want to apply the equilibrium equations. So summation of all the forces in the y direction would be Ra plus Rb minus W is equal to 0. Summation of the moments about A, then you will not have a Ra, that would be RBL minus WA is equal to 0. Okay. So you can also take sigma MB and solve this problem. So you will get a RA as WB by L. You will get a RB by WA by L. Okay, so the reaction forces are now known to you. Now, again, recall the objective is to find the forces and moments at this cross section C. So what you would do now is you would cut this cross section at C, which is the point of interest. Okay, and then you will proceed. So what we'll do now is we will take off in the next class of how to proceed further, because our class is over right now and I don't want to hurry through the next step. So we'll proceed in the next class from here on the same exact problem. Okay, thank you.